welcome everybody to the Chamberlain online seminar in econometrics on Friday, June 26th. Today we're very happy to have the two speakers talking about methods and applications of network analysis. Bryan Graham, who will go first, and Arun Chandrasekhar. Before we start, let me also mention that after this we'll take a break for the summer, and the next seminar will be Friday, September 4th at the usual time. And most likely that'll be on methods for sensitivity analysis, and we'll probably have a couple of talks on that topic. And I think there'll be some more information about that at the end of the seminar. But today we're very happy to have Bryan and Arun talk. And so let me turn it over to Bryan to start off. So actually, sorry, one more thing. We will have questions. They will both talk for about 30 minutes and we'll have questions at the end. So feel free to send questions during the talk, but we will wait with letting you ask them in person and getting answers till 10 o'clock. Then we'll call on people. All right, Bryan, go ahead.
Great. Thanks to the organizers for including me in the program. Some of you may know Gary was my advisor, so it's particularly nice to be able to participate in this seminar. It's not quite clear how I should use 30 minutes to talk about the econometrics of networks. So what I decided to do was use the first 15 minutes or so of my time to just say a few big picture things, largely focused on empirical applications and sort of trying to make a case why networks might be interesting. And then I'll use the second part of my talk to talk a little bit about original research, something fairly straightforward, which I hope I can convey in 15 minutes or so, and also something that in some sense connects to Gary's work on panel data, so I thought might be appropriate. Okay, hang on. There we go. So, this is largely a point I think that was that I came across in Mansky's work a couple of decades ago. The traditional approach in economics has agents interacting via markets, right? And the way we deal with situations where there isn't a market is to create a market. So think about creating property rights for carbon emissions. And that's great. I think our discipline has gotten a lot of mileage out of that perspective. But the reality is a lot of life takes place outside of markets. And furthermore, many markets aren't really anonymous in any meaningful sense, and with prices negotiated and so on. And that's kind of where networks come in. In a basic sense, a network is anything that can be described using the mathematics of graph theory. In plain words, a set of agents and relationships among them. And I think there's a lot of big questions in economics where networks might have an interesting role to play. So Lowry, in a short book he wrote in 2002, postulated that one source of racial inequality in the United States had to do with the differing social networks available to blacks and whites. More generally, there's a long literature in sociology that looks at networks as important for example, getting a job. So I think there's some interesting work to be done in labor economics and the economics of inequality that has a network aspect. Firm productivity. So it's a stylized fact that firms vary tremendously in their productivity. Even within very narrow economic sectors. And of course, firms are themselves embedded in networks of supply chain relationships, R&D collaborations, and so on. And I think there's some really interesting work to be done in that space that, again, involves networks. A classic example where networks appear is in social learning and technology adoption. I hope Arun will say a little bit more about that. And this really can be many things from whether so I get an email from some associate vice provost about once a week telling me about some new software that Berkeley has purchased to facilitate online learning. And the question is, does anyone actually use it? So there's lots of adoption questions, again, that might be usefully illuminated by taking a network perspective. Another area where there's been a lot of work in recently and also historically, going back to Leon Tief, is understanding shock propagation and how a shock percolates through a network, and sort of connecting micro level shocks to aggregate macro outcomes. And then I think another quite interesting area that maybe I'll specifically mention, this one paper by Nicholas Christakis and Fowler has to do with forecasting. So in this particular paper, they used networks to forecast the flu at Harvard University. And there they used essentially the network as a sampling scheme where they randomly sampled individuals, and then they took those individuals and randomly sampled among those individuals' friends. And under some generality, that second step moves you towards an individual that's more central in the network and hence more likely to have been exposed, say, to a virus or some other phenomena which is percolating across the network. And so that's sort of an interesting example of how you might use a network for forecasting and prediction task. Maybe you don't really particularly care about the network directly, but it's still a useful tool for data collection. So I guess my big point is that there's really almost any area of economics where you can find some sort of data structure that has a graph theoretic dimension and some economic question where the two go together. Another thing that's central to networks and why I find them interesting, and it's sort of a theme of all my work going back to my dissertation, is externalities are present everywhere in the context of networks. And externalities are interesting because they generate a tension between individual preferences and social welfare. They create a scope for policies that can lead to modified lead to increases in social welfare. And these externalities arise in the context of the formation of the network. Maybe when I form a tie, I don't take into account the benefits or costs that tie imposes on other agents in the network. And they also occur when we're playing games on a network. So, it may be that I'm choosing how much R&D to undertake, and I don't take into account the benefits of that R&D on my supply chain partners, for example. And that's a feature of networks that I find interesting, and I like and I enjoy modeling. From a statistical standpoint, there's many reasons why networks are hard. And one is that dependence is everywhere. So at a very basic level, there's going to be dependence across the outcomes of any dyad. A dyad consists of a pair of agents. Think of Japan and the United States as trading partners. There's going to be dependence across any dyad sharing an agent in common. So the unobserved drivers of exports from Japan, say, to the United States, are going to covary with the unobserved drivers of exports from Japan to Korea or the U.S. to Korea. Early on in the econometrics of networks, and by early on, I'm thinking, 2013, it was kind of a wild west in terms of how to deal with this dependence. There's been a little more progress, and broadly speaking, two approaches have been taken. One involves exchangeability type arguments that help impose some structure on this dependence. Here, a key result is the Aldous-Hoover theorem. And an alternative approach builds more off a spatial econometrics kind of time series perspective. And it's kind of an open question about I think both approaches are useful, and which approach is useful and where, and then more deeply how the two connect. Another thing that's been interesting, well, I guess I would say initially was frustrating, and now it's become interesting. So, early in my career, everything I did existed in closed form, or maybe it involved like a concave, problem with unrestricted domain. Now I have to deal with computation in my research life, and I've become interested in that. And so one thing about networks is you can't be scared of computation, and then the other thing is that even small data is big data. So you can always say you're working on big data. So I discovered this when I was working on a paper that involved looking at tetrads, and realized that n choose 4 when n is 100, n choose 4 is like 64 million or something, and that was sort of starting to cause my computer to overheat. Now the good news is there's a lot of smart people in computer science and computational biology that have done a lot of the hard algorithmic work for us, so we can sort of use those investments. Here's a network. It's really, the role of this slide is just to provide a gratuitous picture to look at a network. Hopefully, one of these nodes will come up with a vaccine for COVID-19. But when I look at this picture, I'm just sort of intrigued. I want to understand it. I want to understand, why the configuration of the supply chain looks the way it is, and what its implications are for productivity, consumer welfare, market power. I just sort of see a zillion interesting economic questions that I want to know the answer to. So there you go. Okay, so you might be interested in networks, but think, I don't have any network data. Well, in fact, it's everywhere. And becoming increasingly available. So one example where there's been a lot of new data coming out is in buyer-supplier networks. So in particular, several central banks have started to use their VAT tax databases to construct supply chain information, really for entire economies, at least for firms above a relatively small size. So the reference there is to a data set of the Belgian economy, but this has been done in many countries, Ecuador, Brazil, I have to think some more, Japan. So there's increasingly excellent supply chain data out there. It can be difficult to get your hands on, but not impossible. Virtually all of empirical international trade and migration analysis can be viewed as network data sets, so flows of trade between two countries. And analysis of such data goes back at least to Tinbergen. There's been some interest, this is outside my own realm of expertise, but on interbank lending and how what this has to say about financial risk in the financial sector. And certainly if you look at a finance journal, you'll find many papers in that space analyzing such data. I think an area that's super exciting in labor economics and IO is matched employee-employer data. I think this is a huge area where there's tremendous excitement among my colleagues. And of course, that type of data structure is a bipartite network where you have two populations, workers and firms, and relationships among them. And exploring such data and modeling it would fall under the rubric of network econometrics. Another example of such data is bank firm credit data. So you have firms and they have lending relationships with banks. That's been less studied in economics, surprisingly, but I think could be a potentially very interesting area because it connects the real and financial economy. A lot of what people are familiar with when they first are exposed to networks in the social sciences are friendship networks. And of course, these are very important. We're all embedded in such networks, and it's interesting to analyze them. They have implications for human capital accumulation, mental well-being, might be important for understanding inequality. Those data are in some ways more challenging to collect, but more and more researchers are incorporating such data collection into their programs. Another area of network data is collaboration networks, and this is sort of something you can get via bibliographic records, so you can see, which musicians record with other musicians, which scientists write with other scientists. And so with bibliographic data, you can construct a graph of relationships. And this has been done in many cases. Sorry for the circular saw sound in the background, if you can hear it. This has been done in many disciplines, and the two references there are involve economics, where Journal of Economics literature information on collaborations was analyzed. Many other examples, I won't go through all of them, but these examples sort of span the social sciences. There's tons of examples in political science, sports economics, modeling the outcomes of tournaments, certainly public health. It's hard for me to read the newspaper and not immediately start thinking in graph theoretic terms. I guess my big point here is there's lots of data sets out there that have this graph theoretic structure, and you might be interested in modeling such data sets, and in which case you might need to learn a little bit of network econometrics. I'm not going to talk through these papers, but hopefully these slides will be made available online. This is just a few, frankly, somewhat random and idiosyncratic list of contributions to network econometrics. I tried to pick things that I found interesting, and also that spanned some of the diversity of contributions recently in econometrics. And one thing that's been kind of interesting to me is you've seen econometricians come into network econometrics from different perspectives and bring their sort of different human capital and background into things. So there's a line of papers where individuals who have come from the econometrics of games have now tried to apply some of that insight and knowledge from the econometrics of games to networks, and made very interesting contributions. My own work has been heavily influenced by panel data, which of course was in turn an influence of my advisor, and you'll certainly see that in a lot of my research. And each of these papers sort of exemplifies a different background, which is exciting, because as you go into a new area, you realize that you don't have to reinvent everything. You can actually use existing human capital and redeploy it in creative ways. And there's plenty of surveys. Here's a few. I've just finished a handbook chapter. Unfortunately, as I was preparing this morning, I found a typo in it, but anyhow, that should be coming out over the summer. Okay, so what I want to do in the last 10, 12 minutes or so is talk a little bit about a research question that involves networks, and it is a causal inference question. So I thought I would do that because it's a relatively simple and familiar setting, so it's a good place to start. And there's some nice connections to Gary's work, so I thought it would be appropriate for that reason as well. So let's start with the basic question, and this is actually really the question that was buried in the appendix of Tim Bergen's book in 1962, and has been asked again many times in more contemporary research. So you can say, well, does joining the WTO increase trade? Or does, there's many variants of this. Does joining a common currency increase trade? Okay, so what we're going to do is we're going to let WI be an indicator for whether an export or an ego agent belongs to the WTO, and we'll let XJ be an indicator for whether the importer or alter agent belongs to the WTO. This notation is a little more general than we need for this example, since xi equals wi by construction, but the setup accommodates more complicated examples where the ego and alter policies might be different. And okay, and then we're going to imagine we're taking a random sample of countries from some superpopulation, and we're going to observe all 2 times n minus n choose 2 directed training relationships among them. Okay, one thing just to sort of very briefly flag is that this fiction only makes sense if the sampled network is dense. So we really are imagining that we're in a world where each agent meaningfully interacts with all other agents in the underlying population, which doesn't characterize many networks. And you can imagine other sampling schemes where that would themselves create interesting economic questions. Okay, given this setup, we're going to imagine that there's a potential response function which maps policies into dyad level outcomes. So here Yij corresponds to export flows from country I to country J, and this is posited to vary with WTO membership. And we'll just imagine that there's some sort of measurable function which maps policies, and then a exporter and importer specific effect, and then a dyad specific heterogeneity term into the outcome. Okay, and we're going to allow for arbitrary dependence between AI and BI, but the entire sequence will be IID, and it'll also be independent of these dyad specific heterogeneity terms. Okay. Now, if you sort of did some sort of deep dive into the world of exchangeability arguments, you might be able to more primitively justify this type of potential response structure. But to keep things simple, let's just take this as a primitive assumption. Already, you might think, well, this is very structured. It must be restrictive, and that's probably true. But already it sort of has a lot of implications that aren't present in the standard single agent program evaluation model. So, for example, we're going to get covariance across the potential outcomes of dyads that share an agent in common, and also baked into this whole setup, directly but also more subtly, is a complete lack of anything resembling a Sutva type assumption. The setup also immediately generates some new causal contrasts, which might be fun to look at. So we might be interested in the distribution, particularly the average, say, of what exports are when both countries belong to the WTO versus when they both don't. So we might be interested in the distribution of this difference, particularly its average. But we might also be interested in the distribution of the second term, which is a double difference, which would somehow be related to complementarity. So is there really something special about both countries being members of the WTO relative to just one of them? And there's many other more exotic things we might look at. So obviously we're not going to identify any of these causal contrasts at the dyad level. The best we can hope for is identify features of their distribution, and this is for the entirely standard and familiar reason that we only observe the outcome associated with the actual policy pair adopted. And so that's what this slide says here. So the observed exports from country I to country J correspond to the exports associated with a potential response function evaluated at the actual policies, which correspond to whether the two countries belong or don't belong to the WTO. Okay, so given this basic setup, I want to define something which I'll call the average structural function. It should be very familiar to many of you, and then discuss its identification. And I sort of associate this idea, obviously goes back to the causal inference literature and the notion of the average treatment effect, but it also appears in Gary's handbook chapter in the context of averaging over heterogeneity distributions in a panel data setting, and that's very salient here given my setup. So this is a thought experiment. We draw an ego unit at random. In this case, it's an exporter, and assign it, policy little w. And then we independently draw an alter unit, an importer, and assign it policy little x. And the expected outcome associated with this this dyad formed in this particular way is what I'll call the average structural function. Okay, and here's a bunch of integrals which define it. I think I'll skip over the maths. Just focus on the thought experiment as an understanding of the estiman. Now, this type of estiman has appeared in some of my earlier work, particularly work with Hito and Hurt-Ritter, where you in a multi-population setting, you have multiple heterogeneity distributions associated with the different populations, and you need to average over the products of these marginal heterogeneity distributions. Okay, so now I wanted to make a few connections to Gary, and particularly kind of a linear panel data type variant of this setup. So we could imagine imposing a parametric form in this potential response function. And in this setting, the simplest one with x and w being binary takes the form of equation 4, where we saturate the model in the policy variables, and then we introduce the heterogeneity terms in an additively separable way. This has a homogeneous treatment effect type implication. So, for example, that complementarity effect I mentioned earlier would just correspond to delta. And the average structural function would just correspond to the linear regression function in this setting. And I'll return to this example to connect some of the assumptions I'm about to make. Okay, so now what I want to do for the last 2 minutes, show you how to identify this. I will actually stick close to being on time. What I'm going to do is I'm going to posit the existence of two proxy variables, a proxy variable for the exporter effect, which will be Ri, and a proxy variable for the importer effect, which will be Si. And we're going to make a couple assumptions. The first one is a redundancy assumption, which is in some sense almost a product of my notation. So in the interest of time, I'll skip it. And I want to focus on the two assumptions which are more substantive. One is something I'll call a strict exogeneity assumption. So we're going to assume that this dyad-specific component of the potential response is independent of the policies, conditional on these latent unit-specific effects. So this should be a BJ right here. I'm sorry. Write that down. And so what's somewhat interesting about this is it's a conditional independence type assumption, which we're familiar with, but involves conditioning on unobservables. And that's it's not an obvious analog of that in the standard program evaluation setup, but of course it is very much related to things we see in panel data, and in particular Chamberlain's notion of strict exogeneity. So you can see that by noting that this assumption, this conditional independence assumption, in the context of the linear regression model, just implies equation 6, which is very much what Gary meant by strict exogeneity. Another way to sort of see that intuition is to think about the network structure where each agent interacts with n minus 1 other agents as creating a panel-like structure. So for example, we can take this tetrad or within tetrad difference and use it to identify delta here. And this is an idea that is shown up already in the networks literature. So in a thesis by Charbonneau, it also sort of appears in a paper that I wrote a couple years ago. I think in the interest of time, I'll skip the math, but what this strict exogeneity assumption is saying in this context is that all endogeneity between the treatment choice, all endogeneity in the treatment choice is captured by dependence between the policy and these unobserved unit-specific latent heterogeneity terms. And if we could condition on these two latent heterogeneity terms, the remaining variation in treatment would be idiosyncratic, which is very much what we think about when we think about panel data in the sort of most basic primitive linear panel data model. Okay, so I'll go 2 more minutes. To really nail the average structural function, we need to make one more assumption, well, really 2 more. One is a unconfoundedness type assumption. And this is entirely familiar and completely analogous to the type of assumptions we make in the program evaluation literature, which is just saying that treatment choice is independent of the unobserved drivers. Unit-specific drivers of the outcome conditional on the proxy variables, and we know how to reason about this assumption. We sort of have all been in many seminars where there's vigorous debates about whether all pre-treatment confounders have been included or not. I will note that in this particular setup, there's sort of an interesting connection between this assumption, the types of things you going back to, say, work by Hausman and Taylor, and a classic paper by Ariano and Bover. Okay, so I'm not going to be able to go through the argument, but I'll sort of give you a flavor of it. Under this assumption, under these assumptions, what you can do is you can run the regression of the outcome on the treatment variables and the 2 proxy variables. That's a proxy variable type regression, and you can show that if you take that regression function, so I'll use my giant cursor here, if you take that regression function and average over the marginal distribution of the 2 proxy variables, so average over the marginal distribution of S, and then average over the marginal distribution of R, that will recover the average structural function. There's a support condition that we need as well, which I haven't told you about, but that's the basic result. And yeah, so that's that. So here's a support condition. It just has an overlap type flavor. I'll skip it, and what I really want to end with is just a couple comments. So what I hope this example has shown is that you can take some of your existing human capital, your existing knowledge of the econometrics of program evaluation, and redeploy it in this more complicated setting. There's a real literature out there. I mean, there's a whole policy analysis literature in empirical trade, migration, international migration, that you could deploy these methods immediately, and in doing so, you'll find that some of the stuff you thought still applies, and some things you thought you knew don't apply. So here's an example of something that maybe you could think about. So in identifying the average structural function in this context, I made 2 key assumptions. One was a strict exogeneity assumption, and the second was a conditional independence assumption. But if you look at the simple parametric model, there was also this result that within tetrad variation identifies delta, which was associated with complementarity. And so it may be that certain features of the distribution of the potential response function or the average structural function are identified just with the strict exogeneity assumption, and then the addition of the conditional independence assumption may be identified as more structure. So that's something one can go home and think about if they're interested. Of course, there's the issue of estimation. So I have some basic results in the handbook chapter. And actually, estimation here is is super fun. There's all sorts of wild stuff that can go on with rates of convergence, efficiency, whether you get normality, if you like uniformity, there's uniformity things to worry about. So I just mentioned a nice paper by Konrad Menzel on applying the bootstrap to these settings, and a paper that I did with Jim Powell and Fengxi Niu, a PhD student at Berkeley, that looks at density estimation in this setting. And I just mentioned these two papers because I think they're kind of fun, right? You look at the statistics of the problem and you see, oh, this is kind of fun. It's neat. You get some surprising results that aren't necessarily technically hard, although in some cases they are, but are interesting. So if you're into mathematical statistics, there's tons of fun stuff to do. And just to finish up, a couple years ago, if a student came in to my office and said, I want to work on networks, my response would be, good luck with that. It's just too hard. But I feel very differently now, and we can point to several really great dissertations that have been written the past few years. There's sort of a small body of literature, and this is really a fun time to be involved because there's a few things that you can really grab onto. There's been some important developments in statistics and machine learning, but it's still wide open. There's plenty to do, and there's plenty of space to do it. So I think it's a fun area to be in. And another reason why I've really enjoyed it.
Brian,
Okay, I'm done. All right. It's great. Networks are great. Sorry, Arun.
Very good. No problem. Thanks very much. So we'll hold off on questions till after Arun's talk. So let me turn it over to Arun now.
Okay, great. Yeah, thanks for having me. Today I'm going to give you a collection of facts from the applied world, which I hope you guys don't find to be entirely useless. And it's going to raise a bunch of questions for which I have no answers, but smarter people in this room hopefully do. But to get there, I want to start by asking, what is a network? Which coming from me might be a bit weird. It consists, I'll go further than Bryan. It consists of a set of interactions between a collection of units, firms, people, whatever. And in this sense, this entire enterprise is vacuous, right? This is anything you've ever studied in any context. So strangely, like my approach is to think about this. Hold on, why can't I go to the next slide? I'm doing something stupid, right? So strangely, for me, this is all about storytelling. So you're going to decide, given a policy or a scientific context, what features of the problem matter, and therefore what we want to imagine as the network. So for me, it's not fact, it's impressionistic. And sometimes it really feels obvious, right? Think about Twitter. You know what a node is, you know what a link is, you know what a retweet is. But for many questions that you care about, you might care about like social learning and belief formation, offline behavior, slacktivism. Twitter, the graph you get from it isn't even enough to reasonably answer the questions you're going to raise. And when you think about more other settings, things get even harder. So I tend to think about social learning in villages, risk sharing in villages, and then you get into what is a node? Is it a household? Is it a person? Are links bilateral, unilateral, multi-layered, weighted, deterministic, probabilistic? Are they projections of groups? Are they endogenous, exogenous, dynamic? Weirdly enough, here's one that comes from theory. Are they realized or are they potential? Meaning if I give Hito $1 within the last year, are we linked? Or if you ask me, would I have given him $1 had he had a shot, but I didn't because he never had the shot, are we linked? Do you see what I'm saying? So in all these cases, we're going to define our network data or come up with some identification strategies, not in some ex-ante objective way, nothing really is objective, but here we're going to make a strong set of structural assumptions to tell some sort of story. And we cannot escape this. And so it's useful, in my view, to look at reality, to think about what sort of assumptions we should play with. So today I'm going to talk about two themes. These are spaces I work in. One is social learning, and the other is informal institutions. I don't think I have to explain what these are. But here's the perspective I want to take. All models are wrong. And so I want to ask which wrong models are useful in the context we're interested in, And how does that condition the assumptions we want to make when we think about econometrics? So both the applied and theory literature here show that behavior is often highly nonlinear and what I'm going to call not ordered, which will encompass a number of things. The examples I'll give you are first, seeding many, meaning giving information to more people, can be irrelevant for diffusion. Or weirder still, if there's uncertainty, providing signals to more people in a graph can actually reduce social learning. Furthermore, a shock to a market such as partial market completion can actually destroy links much more amongst people that are really far from the shock in the graph rather than those nearby. And these are sort of all striking and particularly weird in contrast with a lot of models we make when thinking about networks. Furthermore, agents systematically do not understand local link structures. If I ask Keto, hey, are Isaiah and Jan friends? He often will have no idea, and sometimes when he offers a guess, he's usually wrong. And that tells us about the games we want to write down to model the graph in the first place. Okay. Social learning. I like to break this into two pieces because they're distinct conceptually: diffusion and information aggregation. Diffusion is what everybody obviously intuitively knows. There are k nodes out of n that are seeded, and things spread through the graph node by node. So here you have one node that's seeded, and over time, as t goes to infinity, everybody gets informed or infected or whatever. Cool. Then you have information aggregation, which is a conceptually distinct point. This is about a machine that's trying to get to either the law of large numbers or the minimum variance estimator. There are k signals given out of n nodes. K could be n. And then there's a box called the graph, which puts together these signals. And the questions in the literature are, dude, did people figure out the state of the world? So if n is going to infinity and k is going to infinity, it's about the law of large numbers. If we're in a finite sample world, it's about the amount of variability in the limit opinion. So you want to look at this. In this case, there's two signals, 3 and 1. So the oracle would estimate the state of the world as 2. Information spreads and starts mixing. And under some learning model I've made up here, 1.89 is the limit opinion everybody has. Okay. So let's take a little toy model of diffusion. Here's a stylized example. We're interested in a binary variable. Do they adopt something or not? So if you adopt something yesterday, you still adopt something today. You have the opportunity to speak with your friends with some probability p, and then you adopt the thing if at least c of your friends have chosen to adopt. This encompasses 4 key concepts in the diffusion literature. The first is duration, how long this system goes. Do you get bored talking about a movie 2 months down the line? Do you get bored about a financial product? It doesn't have to be boredom, anything where things decay over time, but you get the point. The second is complexity of the contagion. How many of my buddies need to tell me that I like something or they like something for me to like it? The third is virulence. How often does the opportunity arise for me to be contaged by those around me? And lastly, the shape of the graph, which I won't really talk about in this talk because it's extremely technical. This raises an empirical question first, which is where are we in the parameter space? So to give you two contrasting examples, if things last forever and virulence is really high and just exactly one person speaking to me makes me adopt, then Matt had an old result and Akbarpur and others have a variation on it now, which is you can basically see a collection of random people and you're good to go. On the other hand, if t is low or p is low or c is 1 plus epsilon, then the entire system is sensitive to seeding in different ways, right? Depending on where you live in this landscape. But we want to know where we live because that's what policy is about. And also, we don't actually have graph data for most of the things we want to study. So how the hell do we leverage these insights without the graph data, right? These are two objectives. Cool. So I'll give you a few examples. So this is a nice paper. Bryan actually cited this as well by Laurie Beeman and others. There are 200 villages in Malawi, and there's a technology called pit planting, which increases yield. Y'all aren't development economists, so I'm not going to talk about pit planting, but there are 3 policies that they look at. First is a policymaker's choice. These are experts, right? Government experts who have done this for many, many years, so they should be pretty good at picking people. The second is they go to the center of the village and they give it to geographically central people. And the third, they collect some graph data and pick central people in some, technical way. They have 2 sets of outcomes, knowledge and adoption of the technology. Okay, so the first result is from a regression of do they know how to pick plant as a function of if the respondent is connected to one seed who they've randomly given information to, or two seeds, okay? And what they find basically is consistent complex contagion, where you have an effect if you're connected to two seeds, but not if you have connections to one seed, okay? The second thing they find is that adoption is a hell of a lot higher than the policymakers' seeding strategy if you seed people who are network central, right? Moreover, seeding people that are network central is better than geographic centrality as well. And so their findings are something like, look, it looks like there's complex contagion and there's definitely variation in terms of who you want to give information to. So it gives us a clue as to where, at least in this context, we live in the parameter space. Okay, that's cool. But we want to get to a point where we can try to do this without having graph data. So you can ask, whom should we pick to diffuse information widely? Maya King has a really nice paper that I recommend reading on this. But the gist of this is you can calculate how likely it is that person J hears from person I by looking at the events that they don't hear from person I either directly or indirectly through 2 paths or 3 paths or all the way to T paths in the graph, right? She sort of calculates this nicely. So Abhijit, Esther, Matt, and I had looked at sort of an approximation of this a few years back. And here's an observation we had. If you look at person J and you ask yourself, how much does person J hear from person 1, person 2, person 3, da, 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 da. This is a column in this matrix. And it has the property that every one of these columns converges to something that's proportional to the same object, which is the first eigenvector of the adjacency matrix. It's called eigenvector centrality in network jargon. It's shown to be something important for diffusion. That's not the point. The key point is that this means that if I asked Hito and then Isaiah to tell me, look, who are you hearing most information from? Who's a gossip? You guys are going to tell me the same person. And it turns out they do in the data. It's actually remarkable. They overlap considerably. And so our thought was, can we try this and use this for policy, right? Name an eigenvector, but really we're asking you to name a gossip. So we went to 2,000 odd villages where immunization rates are really low, under 40%. And there are immunization camps that come to town once every X periods. And the goal is to get people to go there to get shots for their kids, right? This is a super important application. We have 3 distinct arms. So the first is we give reminders to many people. We look at all moms that have been there in the past at baseline, and we give them to a third of them or 66% of them. Not everybody in the village, it's not 66% of the village, but it's a lot, right? It's a decent amount of seeding. Second is we pay people because we're economists and that's what we do. And we pay people according to different functions that theory will tell you to pay people and some huge amounts. And third, we seed random people, we seed gossips, we see trusted health people, and we look at vaccination rates. Here's what we found. So yellow is reminders, and it turns out reminders are not distinguishable from doing nothing, despite many seeds. Second, payment is broadly useless unless you give steep convex incentives with a ton of payment. So very cool measurement, totally useless for policy. India's government will never go for this. Third thing we find is that basically no seeding strategy works. Random doesn't work, trusted health people don't work, except for just this raw gossip thing, which increases vaccination rates by about 26% and is damn cheap. So this at least tells us that this line of thinking isn't insane, and we can leverage it for some policy. Right? Cool. Switching gears to information aggregation. So here's totally incorrect stylized setup of how we might want to think about it. There's a state of the world that we don't know, think some real number. We're trying to guess it for some reason. So my guess, YIT, is some function that can vary over time, that can depend on my identity in the network, which is a function of the probability I speak, the history of observations of other people's beliefs I've had, and the graph structure, right? That's somewhat general pastiche of this. We have 3 concepts that we want to look at, in my view. The first is the shape of the learning function. So this is really an individual level question, but it matters a lot when you stick it in a graph. Are people Bayesian, or are they naive? And if they're naive, how are they naive, right? This affects how information is put together. The simplest example is called degree learning, where I just have no memory. I look at, Bryan and Michael and Hito's guesses from yesterday, I just average them and make an estimate today. Completely stupid, has nice properties. That's why de Groot worked on it in 74. Pretty cool. They're more sophisticated, naive learning models as well. And, we have some nice structural work telling us and experimental work telling us how people might behave. Not for this talk, but the point is this F function matters a lot. It matters in terms of how we think of a pure effect. Second point, this we don't pay a lot of attention to, but it's the endogenous speaking probability, P. Okay. So usually we think about the graph link as fixed, or we think about them as endogenous when we think about something baroque, like trade or, risk sharing. But speaking is pretty endogenous as well, right? I choose whether I want to go ask Isaiah for advice because I'm, confused and he's really smart, but I might be ashamed. On the flip side, I went to grad school with him. He already knows I'm not that smart. So I actually have no shame. So I go and talk to him, right? This is the kind of logic that matters. So if I think about a payoff in general in context, what is my incentive to go seek? Depends on how many signals are out there, my knowledge of how many signals are out there, equilibrium levels of communication, which say how much information is in the town square, signaling concerns. Do I care because of future, interactions, how I'm perceived about being smart or dumb, and the marginal value of information to me, which could be a function of my ability. You write this stuff down and you actually get pretty weird behavior, which we'll come to. But I don't think it's esoteric. I think it shows up in almost any example you want to think about. Some of these things matter because we're human. Last one, network structure itself, right? I'm not going to get into network structure again for this talk, but there are things like homophily, distribution of Voronoi tessellations, all of these like structural features of a graph that matters for how well people work. Okay, we've all written, like I have a paper with Abhijit and Marcus and Emily on Voronoi tessellation, and Matt and Ben have written on homophily quite a bit. Matters how we think about modeling real world networks and network formation problems. The empirical questions from this are, what's a reasonable description of F? And in a given context, what facets of P do we care about? Okay, here's sort of my headline example here. Broadcasting information to more people can reduce learning. All right, so when you look at the top of this, you're going to ask yourself, why on earth would we have done this experiment? And the answer is, if you think about image concerns, it seems obvious. So our context is, in November of 2016, Modi decided to demonetize 86% of the money in India. These are 500 and 1,000 rupee notes. It was quite bad for a variety of reasons. This is confusing for a country with 2/3 of people living in rural areas. But even worse is he changed the rules around this over the next 7 weeks, 54 times before the deadline where it's the last day to exchange your bills. So this is a context where rumors were really widespread, you might imagine. Not for this talk to go into all the details, but 54 times a lot. That would confuse all of us here. So we wanted to give information to try to combat this. And there are two strategies. You can tell 5 people, or you can tell everybody in the village, right? And this is a question for many years I've been getting, which is, why don't you just tell everybody, right? This is why belabor telling 4 people? What's the point? And intuitively, that's true. If you think about any of these diffusion models, like thinking about seeding optimally is a little bit of a silly question. Just tell everybody. The problem is I told you the immunization result already, so you have a little bit of a peak. That's not great, but nonetheless, the problem is if you think about it in practice, if I know that Isaiah knows that I've received information, I have a pamphlet, I saw the TV address, and I still have a question, I know that he knows that I didn't understand it. In contrast, if I know that Isaiah knows that I've been told that Isaiah is the keeper of information, the policymaker said, I deputize you to teach people. This is great. I get to ask anybody anything. Everybody knows I don't know anything. Totally cool, right? So that phenomena, which you guys should remember, is common knowledge. Okay, so the key point is that the extent of this peer effect, so to speak, will pivot on common knowledge. In fact, you'll have a reversal, and that's what we wanted to investigate. So we did an experiment that's 2 by 2. which is we seeded 5 people, or we broadcast 100% of people. And then we varied if this information was common knowledge or not. Common knowledge meant when we seeded 5 people, we told everybody in the community that we seeded 5 people, and we told them that we told everybody. We did this right, so it induces common knowledge. And then with broadcast, it's pretty easy. You broadcast pamphlets to everybody. You put a note that says, by the way, everybody has received this pamphlet and this note. Without common knowledge, it's a lot like the diffusion models. You tell 5 people and you run away. And broadcast without common knowledge is not a real world thing, by the way. You can't, like in practice, things become common knowledge. But if you're doing it before a deadline where currency has to be exchanged, you can actually do it, where you give out pamphlets secretly, like stealth ninjas, and you just don't tell them you've given it to other people. And at least over a 3-day horizon, people don't quite know that other people have received this yet. Okay, so I've told you about the model. Basically, you can write down a signaling model in a network where you can basically show that broadcasting with common knowledge is bad relative to seeding with common knowledge, but if there's no common knowledge, it goes the other way. And so let's look at 3 outcomes: communication, knowledge, and a correct monetary decision. So the y-axis is the volume of conversation, and the x-axis is the different regimes. The first thing to note is that if you look at common knowledge, going from seeding to broadcast reduces communication by 63%. I'll come back to it. You should be able to say, but everybody knows. Why would they talk? So I'll address that in a second. But communication drops by 63%. If you have broadcast, adding common knowledge drops again by 60% communication. But if you didn't have common knowledge, adding more actually doubled the amount of communication. So it's less is more, and then more is more. Okay. The same results are true when you turn to knowledge and you turn to a correct monetary decision. What is a monetary decision? I give Hiro the choice. Do you want a 500 rupee note? This is like 2 days' wage. Or do you want 2 100 rupee notes? Okay. So if you understood the rules, you should take the 500 rupee note and go and exchange it, because that's a lot of money. Oh, worse yet, we told them, do you want 200 rupee notes, 2 of them like a week later, not even now. But if you're confused and you thought that, in fact, you're not like allowed to hold the 500 rupee note, which is what a lot of people thought, you would take the lesser amount. And what we find is that if you seed more people under common knowledge, you have a 40% drop in the rate of taking the 500 rupee note. If you add common knowledge to a broadcast strategy, you have a 50% drop in the rate of taking the 500 rupee note. But if there's no common knowledge, what you expect will happen. As you tell more people, you have more correct decisions. So this matters, and this isn't just about communication, but it shows that learning actually operated severely through the social aspect, where people conversed and the conversations added value, right? We wouldn't have gotten here if we didn't sit and think a little bit about this sort of image, concern, perspective in communication. We have a body of literature on which we build to like get to this point, but getting there tells you how you want to think about response functions in these sorts of contexts, right? This is in, villages in India, but there's nothing special about this. You guys have all been in classrooms where you're ashamed to like raise your hand and ask questions to your advisors or whatever, right? This comes up everywhere. This is just the playground that we work in. All right. Informal institutions. There's lots of examples of this. You could range from, financial institutions, risk sharing, public goods, whatever. I'm going to focus on one example here. I'm going to focus on partially completing a credit market in India. Okay. The idea is there's pre-existing risk sharing networks. So there's limited access to credit. So we have a graph. We know who exchanges money with whom. And to answer my question that I raised in my very first slide, I like to say people are linked if they would transfer money to people in case of a shock. Because if you wrote down a game, that's the right object, right? Not given the shock, it's if you would do it. The question is, what would happen to these networks when you partially complete the market? And it's useful to think about most of the models we write down. They have a radial shock propagation process. What I mean by that is y is a function of a coefficient times a graph times other people's y, and you invert it, you're basically going to have the logic that comes from spatial statistics, where shocks propagate radially. And most of the models that are out there of econometric network formation have this flavor as well. We'll talk about this, and we'll speak to that a bit. So a microfinance institution is going to enter half the villages, and 18% of people join. It's useful to define two types of people, high types and low types. I'm not going to go too much into this here, but high types are people, if a bank entered your village or your neighborhood, you would be likely to join under eligibility rules, or you're likely to hear about it or whatever. A low type is if a bank entered your network, you're unlikely to join. You're not eligible, you don't have a daughter in some age set or whatever, okay? So we can look at subgraphs of any type, but it's useful to look at links and triangles. Links are between high, 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 low, low, low. Triangles are all combinations of triples, right? They matter when you write down theory of cooperation and stuff like this. And if you look at most standard models, many of what like Bryan talked about earlier, where links will be broken and renewed, you have like directed search, you have like matching equilibria with this, you have payoff externalities or support value and friends of friends being friends. They have the following sort of assumptions or results, which is if you look at the dissolution rates of links, links between low individuals basically don't break. In fact, they might increase. If the low types have a drop in their links, it's worthwhile to go find another low type and add a link, right? Because after all, the value of the low's relationship with the low type doesn't change. Neither of them got access to credit, doesn't matter. A high-low mixed type is more likely to break because a high type may not need the low type link, okay? Similarly, if you look at triads, you have some sort of ordering like this. And just for this, just think about it as the extent of exposure. If you have pure low types, there's very little exposure. If you have mixtures, you have more exposure. That's exactly the opposite of what we find. So we look at, this is a data set in Karnataka that we've worked on quite a bit. What's cool is we wrote the paper and wrote the model, and then independently, we looked at an RCT in Hyderabad separately and found exactly the same results. And that came after in a revision, basically. And what we find is that links between low types drop the most, triples between the low type drop the most. So for example, here, mixed types and low type links drop about 8 percentage points, but high types drop about 2 percentage points. If you look at triangles, they're actually ordered in exactly the wrong direction. The triples of pure low types drops the most, followed by a double mixed type, followed by a single mixed type, and the high types actually don't drop. This is inconsistent with most of these models, but what it implies is if you write out like a game, you need a strong undirected search component. So there's two types of externalities in these models. So one is payoff externalities, which is the usual thing, which most people spend a lot of time writing down. And that's cool. It's not to say you don't need it. But the thing that really matters is this like undirected component, which generates, not to say that if Isaiah and I meet, the value of our mutual relationship has changed because he has credit and I don't. Or if Isaiah and Tito and I meet because they both got credit and I don't, the value changes. It's that I know that they're less likely to show up to the town square anyway, so I don't show up, even though the value could have been the same. Right? It's a different network externality. But stuff like this matters, and that actually kills the radial propagation phenomenon. Okay? That's not to say that's not the right way, it's to say other things can matter. Okay, finally. Since we're already a little bit at network formation, it's worth asking, do people know anything about the networks they're embedded in? And so there's a very nice literature in sociology on this. They've spent a lot of time looking at this in a variety of contexts. The best work there looks at if people know the relationships between colleagues in their universities. So Emily Briza, Ali Reza, and I looked at a couple thousand respondents. These is in the same set of villages where we went to Hito and we said, hey, are Bryan and Isaiah friends? And he says, actually, I'm not really sure. And then we say, hey, Hito, are, like Abhijit and Matt Jackson friends? And he's like, I really don't know. This is the kind of thing we want. Or he said, oh yeah, I'm pretty sure they are. So we want to know what he knows about the structure around him. And so the first set of panels on top, the x-axis is the distance between Hito and then the two people we're asking him about in the graph. So distance 1 means they're both his friends. Distance 2 means they're friends of friends, and so on. Okay. What we see is that the share of correct guesses by distance, while it's highest for his friends of friends, he's only correct like 33% of the time. of his direct friends, right? So even though he's friends with Isaiah and Bryan, he's like not that good at knowing if they're friends. He says don't know a lot, actually. And even conditional in saying he knows, he's not that correct half the time. In fact, there's a bias in the estimate. That's even more interesting, but that's a behavioral phenomenon. I don't want to go there. You see the problem here, right? That people are pretty clueless. And it gets worse as you're far, but it's pretty bad when you're close. You can also do it one other way. You can ask, well, like, what if, Bryan and Isaiah, these are superstars. They're super central. We like love these guys. So is he more or less likely to know them? A model of diffusion should say, of course, he's more likely to know if they're linked or not. So the second set of panels orders this by the centrality of J and K, their average, I think. So on the left, it's the lowest centrality. On the right, it's the highest centrality. The y-axis, again, is the share of correct guesses. And as they're more central, he's more likely to claim he knows the answer, more likely to be correct. But still, his overall average isn't great. He's still pretty bad at it, right? So to recap a bit, I think hopefully you find these weird facts to be strikingly nonlinear and non-ordered and strange, but interesting. We saw that seeding more can be not great, can be worse, or it can be non-monotone. Like if you seeded 0 people, obviously it's bad. So the first few are quite good, even with common knowledge. But as you seed more, it'll go back down, is the point. Shocks can propagate in unexpected ways through the graph and change the incentives to rewire in very weird ways that don't look like a lot of models we write down. And there's a hell of a lot of limited information about graph structure out there. And so in terms of at least thinking about model development, I think that there's 4 points that I take away. The first is like, I think contextual goals is important. Like I work on applied work in this space a lot. You've never seen me estimating an endogenous peer effect here. That's not to say people shouldn't. That's just to say the context of what we want to write down as a model is important. The second thing is be careful about assumptions, right? So there's all these papers now relaxing SETPA in like important ways. And a lot of them sort of assume more general forms of monotonicities. And there's lots of contexts in that make sense, but there are probably contexts in which they don't make sense. And it's beyond my pay grade to write it, but I know that that's the demand at least. Third is, look, your model's gonna be wrong anyway. So don't make life too hard. So one way we do it is we're dogmatic about our preferences, and then we have like equilibrium selection problems. But as any theorist will tell you, write a different preference and you might have a nice, unique equilibrium. Or if you take a more realistic assumption about how people have beliefs about things in equilibrium, uncertainty can resolve these problems. Don't make things unnecessarily hard. And finally, I didn't talk much about this, but this is the most useful thing I would be consuming, just models that describe networks. Because like, while we could do gossip to get centrality, we care about other features of the graph. It tells us about economics, but getting data is hard often. So if you could give us a sense of how to get this impressionistic image of the graph, we can actually do things with it and learn things. Thank you.
All right, thanks very much, Arun. I now understand that I don't really know the networks of our profession, and I don't really know whether Bryan or Isaiah are friends. As I'm trying to, so one challenge does seem to be that it's very hard to get the questions right here and kind of figure out which of the parts of these models actually really matter or not. And so actually there were a couple of questions on that. So let me see if I, so let me see if I can get to those questions. Which may take a second to. Okay, yes, Sahid Bello, go ahead, unmute yourself.
Hi.
Oh.
Did not work. Sorry.
Can
you hear me? Yeah. I'm the first presenter. Thank you for organizing the seminar. It's really interesting. So my own question is to the first speaker that talk about the trade network. How does it try to connect because in trade network we have like edges, that's like a link. So how do you try to, what kind of properties do you put in terms of the link? Is it undirected or directed, or what kind of way do you do in order to link it with the model? I'm not sure about that. Hello?
So
Yep.
Brian, yeah, that's
Yeah,
good.
no, thank you. Yeah, thanks for the question. So, um, we've often, the edge, the edge can be directed or undirected. I think in the case of trade, it's natural to think about the edge being directed. So the amount of exports from country I to country J, and real valued. So exports are measured in say millions of dollars. So that's what you would get from your typical trade database. And then from a modeling standpoint, you can use any regression, use a regression function that's appropriate for the nature of the outcome of interest. So if you're looking at a binary outcome, you can use binary regression tools. If you're looking at something like trade data, which is on the positive of the real line, maybe you could use an exponential type regression function. And so that aspect of things is familiar. The difficulty is dealing with the extra dependence that shows up in the network context. So the real challenge is at the inference stage. And there's in some of the references on the slides, there's some references to dyadic regression, which can sort of show you how to calculate standard errors and so on in those cases.
So can I just comment on that? Hello?
Sure. Yeah.
Yeah. For instance, you have like exporting countries that have other importing countries. So it's exporting to other countries. It has a product, it's producing a particular product, but it's going to different countries. So
Sure.
the link between them, it now depends on what kind of the share that is going to different countries. If I'm producing a product, I'm selling to other countries. So the kind of the share might be different. So do you assign weight to the link, or I don't know, the way you model it, how do you calculate the link in terms of, do you assign weight to that link?
Yeah, I think the natural way to think about the trade network is as a weighted graph. So, links are just equal to the magnitude of trade flows between countries. So formally, it would be a weighted graph.
Okay, so there's a question from Nathan Kanan. Go ahead, Nathan.
Okay, thank you so much. Thank you to the presenters and for organizing. So I have a question for Arun, and it's related to something that I've been thinking for a little bit. So regarding the agents not knowing their neighbors, there was some evidence that you had found and that I've read before. I was wondering how you think of incomplete information here from the modeling point of view. For instance, how do you think about an agent's choices when he doesn't know their neighbors, and then he or she might have to put beliefs upon someone they don't observe, and who that person they don't observe is connected to, and so forth. So beliefs upon beliefs in settings of incomplete information from a theoretical and maybe empirical point of view. Thanks so much.
No, that's great. So the good news is there's like, so Michael Young, for instance, has a paper on this. Actually, this is sort of predates the paper that Bryan referred to. It's exactly where you are think about them as effort, right? So it's like a game in which people are going to have shocks and have some like payoffs that could be, their average payoff is known, and there's like unobserved shock, and then you're just going to put in some effort. And he's worked that out, and it has like all the nice properties you'd want. It's point identified. You can consistently estimate parameters. And the paper I talked about here, like Alireza, Emily, and I work out a toy example to do that. It simplifies things actually, because you don't have to like think about like details of a graph structure and have like many graphs being equilibrium possibilities. Like, you're just saying that there's uncertainty. I don't know the epsilons, and so I'm going to draw people from the population essentially, and then we'll mutually consent. And so I just, you know, pick intensities of interaction that way.
See. Thank you.
Yeah, but there are two examples worked out. That was sort of a vague answer, but like, yeah, I think it's not like something where you have to reinvent the wheel.
Sounds good. I'll just have a close look. It's just I have this understand the intensity margin. When we had to work on something similar, I mean, the nice property is that you end up only having to look at local interactions because you can just endow in the structure. Depending on beliefs, that will be enough for me to consider the people I do observe. But on the other hand, in this intensity or this redrawing, I guess I have to look more into it. Like is the redrawing randomly? Is it related to the underlying network proportionally to the network that exists, and then I'm redrawing? But maybe I'll look into it a bit better.
I mean, those are all like, Michael Koenig has one where you like arrive to a space and you see some people, and then you like put in some set of links that match based on something. Like the playground's really big. So I don't have like any specific advice without knowing your context. But I guess what I'm saying is there's a set of stuff, starting with Michael's paper on this, that actually works this out. And I haven't actually seen his stuff being used. I could be wrong, but like usually when we talk about the canon of papers here that Bryan outlined, if I'm not mistaken, Bryan, I don't think like that's one of them that fits into this general canon, but that might be my favorite one in this space because it's sort of the least absurd.
Okay, awesome. Thank you so much.
I have a question there. Sort of Bryan kind of brought up this setting where you could really get a lot of the information by focusing on these tetrads, kind of these small groups of the individuals, kind of some of whom were in one treatment group and another, and somehow kind of difference out the individual components. That kind of seems to tie in very much kind of with the panel data literature and things. Sort of you see that as a general strategy that's kind of in a lot of these network settings, we should just conditional small groups and kind of look at partial likelihood type arguments for these smaller groups.
So in the handbook chapter, I spend a lot of time talking about composite likelihood type ideas. So this idea, maybe you can write down the likelihood for a subgraph and then form criterion functions by aggregating overall subgraphs and then sort of dealing with the dependence across the summands in the criterion function ex post. And I think that's quite workable. So you may not be able to model the full joint distribution of outcomes, but you can model some subset. And then you might be able to use tricks you already know to model that subset. And that's sort of one maybe uncharitable description of my own research strategy. I do think there's a lot of interesting questions that remain unresolved. So like, what's the information loss associated with going from, say, a full likelihood for the network to a composite likelihood? I have intuitions and conjectures, but I don't have answers. But yeah, absolutely.
All right, so feel free to send more questions. And this is to the audience, but let me, in the meantime, have another question for Arun, because at the very end you kind of brought up this idea that maybe we're making these models too complicated and we're trying kind of too hard to get these things right. And maybe it doesn't really matter. It shouldn't matter to me whether I actually know whether people far away from me are friends, kind of the network structure far away doesn't really matter. Somehow I need to kind of figure out whom the people are that I'm connected to, who are influential, whom I should listen to and whom I shouldn't. And maybe I shouldn't be too worried about the endogeneity in some of these things. But so how are we going to, which parts of the models do matter, or how are we going to figure out which parts do matter?
So I think, I think the first part of your question is wrong to begin with, which is, are we going to get this right? No, like the way you're going to write it down is wrong, right? So I wouldn't start that way. Like you're not going to write it down in a way that's correct. So I think it's useful to think a little bit about what is the object that we're going to study. So like, let's take a village, for example, right? Like a risk sharing village, like quite seriously. We know this thing moves over time, right? Like, let me just do the survey for like, 3 years. Like this thing is going to change for a variety of reasons, right? And so, you know, I know the way we think about it is we think about this as like, a nice equilibrium structure that at least in this moment is static, and we want to study the game that generated that. I'm not sure that we're seeing that. I think we're probably seeing like a draw at time t on something that's like evolving over time. And that then asks very realistically, if you kind of get rid of, if that's your perspective on the abstraction, then the details of like, why and how am I changing what I'm changing, stepping from t to t+1 actually matters. That actually matters more than imagining that we're at t infinity. I'm not saying that that's bad. This is coming off that way. That's not my point. Just depending on the nature of your question, it might not be the most useful way to model it, right? And so maybe a good representation of it is to say, look, like people in villages are deciding who to join ROSCAs with, these rotating savings credit association. And they also like playing cricket. And I might think about the graph of playing cricket in the entire village constructed in equilibrium, or maybe, you know what? I kind of look around and say, hey, these people are available. Let's go play cricket. Also, I participate in ROSCAs with some people. And then when a surveyor shows up from JPAL and asks you about who you're linked to, you see a projection of this object, right? Is that a correct description of the world? Totally not. But it's a different way to get at this object. And I'm not sure that it's not more useful in at least this context that I talked about, right? So I think that's my perspective, that we're not going to get it right. The other thing I don't see at all is some of this relies on informational assumptions, and the theory literature and experimental literature in networks worries a lot about how people process information, right? It deviates strongly from Bayesian learning. But then when we go to write down our models of how these things are formed, what do we assume? We assume exactly the thing that we reject in the other parts of the same subfield. Again, this is for like smarter people. I don't know, but this is a thing that we need to think about.
Can I just add something that popped into my head? So even at a very basic level, we are just trying to formulate a regression function for a dyadic outcome. You can, just like in the case of IID data, you can just compute the linear regression function and think about it as a constrained optimal predictor in a mean squared error sense, and similar results apply here. Things can get pretty exotic sometimes in the distribution theory about whether you have correct specification of the regression function or not, but I think it's descriptive analysis can be done, and we can do inference on parameters of such models, and that's fine.
Any more questions from the panel here or the audience? Is there any thoughts on kind of where we should be going with this literature? Kind of, Arun's comment kind of seemed to suggest that we shouldn't be that worried about trying to worry too much about these more complex models, and we should try to kind of tie the things very specifically to the questions. But part of the difficulty is that in this literature, the set of questions seems very large. It doesn't. It's not a very. Unlike in other literatures, there's no small set of canonical questions for the literature to focus on. I think that makes it more challenging.
Just one comment on that, which is, I mean, if you think about it as a literature in a field, that's true. But if you think about it as a tool, that's not true anymore, right? I don't think about it as like a field, because then you move to this canonical model perspective. but it's just a perspective, right? It's just a way to go into other places. It's like behavioral in a sense. It's just a perspective, is at least my view.
Okay, so there's an additional question from Arthur Lubell. So that's Arthur. Can you unmute yourself? Yeah.
Yeah.
Go ahead, Arthur.
Yeah, so it's just mainly a question for Arun, which it seems like he's talking about measurement error, but there's two kinds of measurement error. There's measurement error by the members of the network, and there's measurement error by the econometrician. I'm wondering how he thinks either of those things are interacting. He seemed to be mostly talking about how members of the network themselves don't know what the network is like.
Yeah. Ooh. So I guess at a minimum, the relationship is probably, if we're writing down how people interact and we have reason to believe that agents are interacting in a way where they make measurement error, then the way we write it down must incorporate that. Otherwise, we're misspecified, right? Otherwise, we're made. So I think, Arthur, I don't know if that makes sense, but that would be my perspective at a minimum. Like, we seem to be somewhat dogmatic to not write down deviations from canonical setups about how they say process information, even though we know they do empirically. And so then by definition, we're misspecified. I believe. Correct me if I'm wrong.
I mean, I think that sounds right, but if they're wrong and we're getting our measurements by asking them, then we're wrong also. And separately, we could be mismeasuring just because we're mismeasuring. And I guess maybe you're just saying that we need to model both.
Yeah, exactly. It's not a very deep thing. Like, I'm saying we need to model both. And it's a little bit of a plea maybe to think like related a bit more to the somewhat extensive both lab and field experimental literature and stuff like this.
All right, so let me just call on Alejandra the next to ask a question. Go ahead, Alejandra.
Thank you. So I would like to ask to Bryan, what are the main challenges of extending models, in particular those that are derived from panel data models on networks, to a setting where you have directed networks? In particular, I'm thinking about this bilateral heterogeneity term. Usually in social networks, we assume that it is symmetric. So I would like to hear more about the challenges from departing from this symmetry assumption. Does that make sense, my question?
Yeah.
Thanks.
I don't. I don't have a general answer to that question. I'm kind of a guess and check researcher, and I feel like I'm approaching sort of some understanding where I'm able to forecast or make more coherent conjecture. So I certainly found intuitions and insights from panel data, many of which I learned from Gary, to be very useful in this setting. It's never been entirely straightforward, certainly ex ante and not even ex post, to apply these methods. However, I do think there is something deep there. Panel data was interesting in the 70s as it was first becoming available, and actually as Gary first started working on it, because it allowed the incorporation of unobserved agent-specific heterogeneity, and also because it had more complex dependent structures. So it sort of raised new identification issues and new issues regarding estimation, inference, and efficiency. And I think the exact same sort of ideas going on here. And there are some parallels, this sort of pseudo panel structure where you can think of each agent interacting with other agents. However, we can't take that too far, because in a lot of networks, I'm not really choosing whether to link with all 6 billion people in the world. There's some sort of arrival rate at which I get a chance to form a link with some random set of people, and that's a much more complicated and interesting model. So, but I think I think using ideas from panel data is a reasonable place to start. Yeah, I don't know if I have.
Would you say that the main challenge is that these directed networks, say trading networks, are sparse, and that is not compatible with panel data setting? Would you say that assertion is somewhat correct or something?
It's sort of more complicated than that. So I found that in sparse network settings, panel data ideas that involve conditional likelihood ideas where you use a transformation of the data which eliminates heterogeneity, to be more useful than, say, joint estimators, where you jointly estimate the heterogeneity terms along with the common parameters. More generally,
right. You're talking about tetralogit versus the other one. I forgot the name. The other
sure,
one.
That would be one example of a more general principle.
It'd certainly be interesting to see more work in that direction. And I think kind of the directed graphs have been a little underexplored still in this
absolutely.
literature. All right.
Can I ask just one very small follow-up question?
Yeah, we're running a little bit out of time here, so it's because I need to make some closing comments. So
sure.
let me.
Then I can ask later.
Yeah. So as I said before, first of all, let me thank the speakers, Arun and Bryan, today. As I said at the beginning, we'll be stopping we'll be taking a break for the summer, and the next seminar will be, as is on the screen now, the September 4th, where we'll have 3 presenters talking about sensitivity analysis: Isaiah Andrews, Stefan Bonhomme, and Tim Christensen. So I hope you guys have enjoyed this seminar so far, and that people will be back in September.